Is the volume of data that you have to manage outgrowing your database infrastructure? Have you heard about NoSQL database alternatives, and are you wondering if any of those would be a fit for your situation? Have you considered using open source NoSQL databases such as Redis or MongoDB, and wondered whether cloud versions of those would be a better fit, or cloud alternatives such as Amazon DynamoDB or Google Cloud Bigtable? We're going to take a look at the different aspects of NoSQL databases. We're going to understand the types of databases such as key value and document, and we're going to apply them to common business scenarios. In this course, we're going to be working with a number of public cloud services, and there are some best practices for working with those while you're learning. We're going to be working with Amazon Web Services or Google Cloud Platform Services. You may choose to use other cloud vendors such as Azure, and your process will be slightly different, but these best practices still apply. First, I recommend that you create a dedicated learning account if possible. This way, if you started some services that you don't need for your production business, they're going to be completely separate. Also, if the particular vendor has a free tier, so some of their services can be tried out with no cost, I recommend using that. It's often marked in the console, so you want to take a look when you're starting up services. And if the vendor has the ability to create a cloud budget and an alert, I recommend setting that up. For example, in Amazon, you just go to the cloud budget section and set up the alert to notify you. Usually I use email for that, but you could use the text as well. And I set the threshold to a small amount, usually around $50 US, so that if I forget to turn off a service, for example, I'll get a notification and not a really big cloud bill. And last but not least, it's really important when you're done trying out whatever service you're learning that you turn it off and or delete the instance when you're done so that you don't have any excessive charges. To get us started taking a look at NoSQL, let's consider this quote from Craig Mundy. Data are becoming the new raw material of business. The most important part of this is the word are, multiple types of data. And it's really for this reason that the NoSQL movement and set of databases was born. To start, we need to see where we came from and what is the state of data today. So when we think about managing data, we of course think about data as files on file systems. We think about data as tables, more specifically relational tables, in relational database systems such as SQL Server, Oracle, or open source systems like MySQL. The data in the tables is in commercial, such as Oracle, or open source RDBMSs, or relational database management systems. Data these days is also in data warehouses. These are specialty built systems designed for fast, large amounts of data that are retrieved via aggregate queries. Traditionally, these systems were called OLAP, or Online Analytical Processing Systems. And this is in contrast to the data in commercial or open source RDBMSs, which have been categorized as OLTP, or Online Transactional Systems. So when we think about storing data in file systems, we need to consider key aspects of working with those systems, because NoSQL was created to overcome some of these limits. So the data is stored on some sort of file servers. Traditionally, they were on-prem, but increasingly, they're in cloud-based services, managed by network managers rather than data professionals. Although, as these file systems move to the cloud, the emergence of DevOps or even data ops roles is something that I see occurring. Particularly on-prem, to optimize for increasing amounts of files, the network managers would configure the hardware. Contrast this with key aspects of relational database management systems, or RDBMSs. These systems would use the SQL syntax, very notably join syntax, to join information between multiple tables to retrieve results, and CRUD, or create, read, update, or delete modification operations, would use database schemas and often transactions. And the reason I'm calling these aspects of RDBMSs out is that I know that most of my viewers will probably have a RDBMS background, but some may not. Some people coming just out of school have never actually seen a relational database. And so I think it's important in context when we start talking about what we have available in contrast to this to think about where we're starting from. Also, you generally optimize these systems by adding indexes or indices to the tables or by adding hardware. Key aspects of data warehouses include the following. The data is modeled using a very specific methodology. Generally, it's called a star schema, which represents a star, if you will, a central denormalized table, which is called a fact table, and then related smaller tables, which are called dimension tables. This becomes very important when we look at some of the new NoSQL alternatives, which don't require this kind of rigid schema modeling. Queries do not use joins generally because the majority of the information is pre-joined and pre-aggregated in some cases in the fact table. CRUD operations use batches rather than incremental or streaming inserts. Traditionally, data warehouse systems were designed for very infrequent updates. In my experience, this is often done once per day or even less frequently than that. And you would optimize data warehouses using aggregations or by using hardware. Now, I opened this section talking about data as a plural entity, and a key situation in the world of data has been the addition of a new type of data, which is generally called behavioral data. So what is this? So first of all, it's data that's not transactional. So I like to make an example with a retail store. Traditionally, if you sold something, you would capture that and you put it in your relational database because you needed to have a transaction. Let's just call it, we're selling sweaters. Was the red sweater sold or was it not sold? You wouldn't capture the fact of if someone looked at a red sweater and decided they might purchase it later, or they looked at it for a certain period of time and then put it back. You would only capture the transaction. Now, behavioral data is designed to capture those activities. In our example about the red sweater, what was the footpath the customer took in walking over to the red sweater? Did they go directly to it or did they walk around the store? Did they pick it up? How long was it in their hand? And you might say, well, this is impossible. It's really very possible. Some of the merchandise tags in stores have had motion tracker sensors for many years, and the foot tracker traffic has been captured by overhead cameras as well as by purchasing information from customer cell phones and many other ways of capturing that information. And as I was just explaining, data is collected via devices, sensors, cameras, all kinds of different methods of collecting the data. If you're on a website, collected by looking at where you click, but in some cases, if your webcam is turned on, even by where your eyeball lands on the particular page. So there's an increasing methodology in capturing this behavioral data. And as I mentioned, this data was data that was previously not collected. It just wasn't seen as important. There weren't all these capabilities for capturing this data, but the data has increasingly been something that businesses would find value in. So what are some more examples of behavioral data? From websites, as I was mentioning, not only can and do many businesses capture click tracking, where you click on the particular page, and there are, in fact, actual businesses that will set up A/B testing to help to get customers to perform the action, whether it's downloading or buying, by showing different versions of pages and tracking where people click on those pages. And as I just was mentioning, if there is overhead cameras or some sort of camera associated, there even is this capability to have eyeball tracking as another example. Another use case is for mobile applications. User location can be tracked, user activity. It's really interesting exercise to, if you use Google Maps and you have location turned on, to turn on the timeline feature. Not only will Google track where you have been, but they will estimate what you were doing in transit, I think based on the accelerometer in your phone. If you are a real data nerd like me, you can download that data as a JSON file, and you can take a look at where Google has been monitoring that you have gone and what they think that you've been doing, if you've been walking, driving, so on and so forth. So the key aspect of this is Relatively recently, the amount and types and, importantly, volume of data that are available has increased exponentially. And because of this, new types of data solutions, most notably NoSQL, have been designed to address working with this data more efficiently and effectively. So what has really driven this growth of behavioral data? It's what is commonly called web-scale data. So what does this mean? It's behavioral data collected at a massive scale, a scale we've never seen before. And this was first driven by the big search engines, most notably Google, but Bing and some of the other ones as well. Many of the products that we see today as NoSQL databases were developed by people who worked at Google at one time or based on technologies that were designed to address these scalability challenges because of the amount of data that Google was collecting, not only to index the web, which in some ways could be argued was transactional, but increasingly behaviorally through their Android ecosystem and through their applications such as Maps and so on. Again, along with Google, the other big social players like Facebook, Twitter, and LinkedIn joined in this collection of massive amounts of behavioral data and then turning that into business value, either by monetizing that data or by using that data to increase stickiness of their sites and so on and so forth. Additionally, over the past few years, the type of data that's being collected as behavioral data has grown exponentially in volume because it's, in addition to text, it's picture and video based. Particularly as of this recording, newer services like TikTok, which is similar to Snapchat for the younger generation, generally, Instagram, and so on. These types of services not only collect the text data of where you are, what you're doing, what you're looking at, but they collect it in the form of picture or video, which is, of course, a much larger scale. Speaking of scale, it has been estimated that Google is working with 20 petabytes per day in 2019. So this data growth driven by web scale behavioral data changes everything. And it's really where the NoSQL ecosystem came from. File systems and relational databases no longer work at this level of scale. And in this course, we're going to look at how the NoSQL ecosystem has evolved. I've been working with it for over 10 years. It's been really interesting to see kind of the loop. And this is the second iteration of this course. The first iteration was about 5 years ago. And there's been quite a bit of change in the NoSQL ecosystem, most notably with the growth of public cloud services. And the services that I choose to show and that I now use with my customers has substantially changed over this period of time as well. To address this data growth challenge, the addition of NoSQL databases has been a common pattern for really many years. However, the way it's implemented today has evolved. A key reason to take a look at NoSQL databases is because at web scale, relational database performance suffers. Now, we'll be exploring in more depth why that is as we progress through this course, but it is important to consider that for certain business cases, certain data volumes, certain data types, relational database is not the most efficient answer. At web scale, it becomes too expensive to scale these relational database systems in particular. Non-relational or NoSQL databases were created to address specifically this problem many, many years ago by vendors such as Google and Facebook, as well as other groups of developers worldwide. NoSQL databases live in the space between files and relational tables. Some people like to talk about semi-structured tabular data or quasi-relational. And we'll be looking at specific types, whether it's JSON type of data, XML data, or other types of data. Oftentimes, that data comes first from files and then is loaded into proprietary storage format for the particular NoSQL database instance type. Now, the NoSQL ecosystem is predicted to grow by this particular citation from 2015 to 2020 at a very, very fast clip, 38.6% top in terms of new types of IT systems. And I think there's a number of reasons for that. The first of which is the maturity of market. When I first started working with NoSQL so many years ago, it really was the Wild West. At one time, there were over 150 different types of NoSQL databases, and it was really kind of crazy to try to figure out which ones were viable, which ones to use. And in general, the market has really calmed down and consolidated, and I think that this is reflected in the adoption of NoSQL. So when we think about what data are today, in addition to file-based data, which we would see everywhere from laptops to file servers, whether they're on-prem or in the cloud, and tabular data in relational databases or data warehouses, the new type of data that's so important to consider and is really the driving force behind NoSQL is behavioral data, which is sometimes called event data as well. And that data is most typically put into some kind of NoSQL database. Here's a quote from Ankala Subbarao to start this section on learning more about NoSQL. Processed data is information. Processed information is knowledge. Now, storing data with NoSQL, in my opinion, can be relatively easy, although there are some challenges as compared to storing in a proprietary relational database system, for example, if you're new to it. So NoSQL storage systems are used for files or semi-structured tables, as I mentioned previously. It's not used for relational tables. There is no concept of normalization or relating the data between tables. So first normal, second normal, and normal form for those of us that come from that background. There is no normalization in the majority of NoSQL systems. It doesn't use relational tables, and really importantly, it doesn't use schemas. So there's this concept in NoSQL of schema on read rather than schema on write. And I've seen a lot of dev teams go wrong with this because they are under kind of the mistaken impression that either they can write their own sort of schema layer, and although that can be done, you really want to use the best fit solution for the data that you are working with. So if you are working with mission critical relational data for which that you need transactions, you do want to use a relational database system. And NoSQL storage is often specific to the NoSQL database type. As we'll see when we get into this, there's general categories such as key value or document NoSQL databases. So if you have data coming in the shape of, let's say, a document, you will tend to choose a NoSQL database from that category. And data types often will drive the selection of the particular NoSQL database. Not always, though. Now, querying data with NoSQL, I think, when you're new to it, is much more challenging, particularly if you come from a relational background, because in the name, it does not use the ANSI SQL query language. And again, notes from the real world, I've seen a number of dev teams underestimate the amount of effort it's going to take to learn how to query data with NoSQL. So we're not using the SQL query language. Sometimes it's like it, and it's often called something QL. So in the case, for example, of a NoSQL database called Cassandra, you use CQL or Cassandra query language rather than SQL. But that's illusory. It really is not similar structurally or in ease of use to SQL in my experience. NoSQL doesn't use relational tables and joins. Again, I'm emphasizing this because if you're coming from that background, it's almost, in my opinion, more difficult to unlearn what you know about relational databases. You just really have to start with beginner's mind and think, this is a complete different system. It's not like that. It's something new. And NoSQL queries are optimized by the system type. Again, this is an area that I did quite a lot of consulting over the years, and people will become really frustrated because, of course, in traditional relational systems, you optimize from pretty well-known methods like adding indices, partitioning tables. And although some of those methods work in some NoSQL systems, it is really very specific to the particular system. So a complexity of working with NoSQL at scale, which is the reason you use it, is committing to understand, based on the provided documentation, how you're going to optimize. I've had a real lot of consulting work around this because, again, teams most often in startups, they just didn't understand. They said, oh, we'll just use open source NoSQL database X and it will be free and it will be easy. And then when they became successful, their database blew up and they had no idea how to fix it. And this really underscores my last point. Learning NoSQL query and optimization requires time. So what you may save in licensing fees, if you are choosing this for storing a majority of your data rather than, say, something like Oracle, you are going to have to pay in terms of time in your dev team learning how to work with a particular NoSQL database. I really cannot stress this enough in my experience working with these different databases. I have worked with probably 20 different NoSQL databases in my professional career, and this is really the key difference between success and failure in returning business value. Committing to the time to learning the proclivities of the particular system is really a non-negotiable aspect of getting value out of NoSQL. So let's consider how NoSQL can overcome file system limits when we work with web-scale behavioral data. NoSQL uses proprietary storage methods, and as I previously mentioned, you can think of it sitting on a scale between file servers and relational database systems. Now, in addition to working with file systems, of course, there is an entire ecosystem designed to work with data which is represented as files at massive scale, and that's the Hadoop Spark ecosystem. Hadoop Spark, you may know, uses its own proprietary file storage system, commonly called NTFS, or increasingly these days, a new type of storage system, which is called a data lake. Now, I've done a number of courses in the library on the Hadoop Spark ecosystem and data lakes. So you may want to search on those terms if you're interested in understanding more about those use cases. In particular, I've done work with genomics or bioinformatic research, which is file-based, and worked with Hadoop Spark, and those use cases are discussed in those courses. So data lakes increasingly operate on not only distributed file systems, but cloud-based, such as AWS S3 or Google Cloud Storage file buckets or Azure data lakes. So there are a number of services that have been released relatively recently over the past 12 months by the cloud vendors to help to operationalize data lakes. So on the highest volume end, in addition to considering NoSQL, I often will consider Hadoop Spark data lake cloud-based architectures for massive file-based data solutions. Now, NoSQL, in terms of overcoming RDBMS limits, we're reminded that NoSQL doesn't use SQL syntax or joins. And because of this, throwing massive amounts of quasi-structured data into tabular structures can be much more efficient using NoSQL systems. NoSQL CRUD, or create, read, update, and delete operations, do not use schemas, as I mentioned earlier. So it's schema on read rather than write, or transactions. So they're faster in many cases than relational database CRUD operations. And NoSQL optimization, as I was discussing in a previous movie, is unique to each type of NoSQL system and requires significant dev time to learn if you're new to the NoSQL system. Now, when we consider overcoming data warehouse limits in terms of NoSQL, we have these considerations. NoSQL does not use, as we were mentioning, any sort of schemas on write. And in particular, traditional data warehouse systems had very strict schema modeling requirements, which is something that I'm really familiar with. Previously, many, many years ago, I not only worked in this area, I wrote 3 books on the topic. So it's interesting to see how technology advances and improves. And I'm sort of happy to say that a key limit of data warehousing, which was these somewhat restrictive star schemas, has been superseded by some of the NoSQL technologies that are now available, which provides, again, better value more quickly to the customers. NoSQL does not use aggregations, which is the data warehousing method of indexing or duplicating portions of the data stored in the warehouse for faster queries. Again, this process of determining, building, rebuilding, defragging aggregations, although helpful in data warehouse performance at its time, really is a set of technologies that, again, have been superseded by some of the advancements in NoSQL. So it's kind of exciting to see, actually. And NoSQL often, not always, does not use custom hardware. Data warehouses were notorious for this, and comparatively expensive vendor commercial licenses. Now, again, there's always exceptions to this case. As NoSQL becomes commercialized and grows up, there are some relatively expensive license situations out there. But data warehousing, in traditional data warehousing in particular, was notorious for almost prohibitively expensive licensing, which is no longer the case with NoSQL solutions. Next up, we're going to get an introduction to the CAP theorem. This stands for consistency, availability, partitions, or partition tolerance. And the thinking is that a database system can have two, but not all three of these capabilities. So what are they? Consistency has to do with data and the consistency of the data being written and being read. Now, in relational databases, we have transactions by default, which can be summarized by saying if we had two tables and we want to take something out of one and put it into another, then we can combine or group those two statements as a transaction. They can either all succeed or all fail. Banking is the classic example here. Generally, in NoSQL databases, transactions aren't present, although there are exceptions that we'll see. It's important to understand the performance overhead that transactions cause. In terms of availability, that means that the system will have multiple copies in case one part of the system goes down. There's a redundant copy. Again, there's a cost to this. And partitions increase scalability because you can simply add more nodes to serve up more of the data. Now, you can already start to see, even if you're new to this, how these different abilities can be in conflict. Let's look at them in terms of our systems. It is, of course, an assumption that we're going to have more than one partition when we have this discussion. And, of course, as we mentioned, with one notable exception that I know of, we can't have all three in one system. So if we think of our consistency and availability and not partitioning is really what we get with a relational database. Consistency, we get transaction isolation and repeatability. And I talked about the banking application. And availability, we can have clustered or duplicated servers with up to 5 nines of uptime. Of course, that's a non-trivial thing to do, as all of us who have been DBAs know. There's quite a bit of work around that. As I mentioned, though, key to this is not easy to partition. It's expensive to scale. Let's contrast that with availability and partitioning that's classically present in NoSQL. So partitioning, fast and globally scalable. And if we took a mobile gaming application, we simply add more nodes. And if the data isn't consistent all the time, our game players will just hit refresh. It's not, affecting their bank account by contrast here. And we can have high availability, we can have clustered servers, and we can have high uptime. But as I just mentioned, not transactionally consistent. Of course, Google always has to have the exception case. And so of the products that I'm aware of that are commercially available, the only thing that claims to be and appears to be having all three of the CAP capabilities is Google Cloud Spanner. Now, as you might imagine, this capacity is expensive. And although it's very exciting, I only recommend it to use for Google scale relational data. Now, if you're curious like me and wondering how they actually did this, I put a link to the white paper that talks about how they created their own time management system called TrueTime, which is key to the ability to have globally scalable transactional consistency. It is a really compelling read, but it is the exception case. Everybody else just gets 2. Google gets 3. So now let's apply the CAP theorem to NoSQL databases. NoSQL databases that we've been discussing are designed to overcome the limits of scale. And of course, having the C or the transactional capability slows databases down. So they're generally AP, available and partitionable. And they're designed for the types of data they serve. So whether it's some kind of file or some kind of document or something else. They're created originally by web scale companies and they were open sourced. Subsequently, they've been commercialized. There's been new types of NoSQL databases created by non-web scale companies, but you can still see the lineage of the Googles, the Facebooks, and the LinkedIns in the NoSQL databases that we use today. And they live between files and relational tables. So if we think of what data are today, we think of files, and so we think of laptops, file servers, the Hadoop Spark ecosystem for massive amounts of pure file-based data, which had been NTFS but are now moving towards cloud-based data lakes, object stores such as S3. We have tables and relational databases. We also have our data and data warehouses. We see that still, the OLAP star schemas. And of course, the area we're focusing here is behavioral or event, which is the NoSQL database world. Now, as I said, I've been working in the NoSQL world for many years, and I've seen some trends that are impacting the NoSQL ecosystem that are going to be reflected in what we cover in this course, significantly different than the original version of this course. And the number one trend is the prevalence of cloud and cloud technologies. I do all my professional work in cloud now. I know that there are some situations for which cloud does not fit, and those would be cases where on-prem NoSQL would be still a viable option. However, I like to talk about my experience in my courses, and I've been 100% in cloud for many years now, and I'm seeing cloud vendors increasingly provide professional levels of support, integrated support. For example, GCP having Stackdriver support, which is their monitoring solution for open source NoSQL databases, kind of creative and interesting. And more specifically to this course, the cloud vendors have created competitors to the open source NoSQL solutions. So, for example, MongoDB is a very popular document database, and we'll see in this course how it's being not only supported, but also alternatives are being provided from vendors like Amazon. And of course, it wouldn't be a cloud course if I didn't talk about serverless, and this is impacting NoSQL as well. Serverless to me equals usability. Now, there's a hot discussion about, vendor lock-in versus usability and flexibility. However, I have to tell you, I'm seeing over and over, especially if NoSQL is new to you, that having a serverless option gets you up and running faster and gets you to value faster. So it's not always the correct approach, but I am going to emphasize serverless cloud-based NoSQL when it's available because I'm using it. Also, maturity of the ecosystem, multiple types of NoSQL solutions in one product. And this makes it a little difficult to present this as an introductory course. Back 5 years ago when I created the original course, if you were looking at a document NoSQL database, it provided documents. Now that same document database will provide different types of data and different types of capabilities. It might have transactions, it might have indexes. So as the market has grown up, the products have grown up. And what I would encourage you to do, and I'll provide you with resources throughout the course, is if you're interested to go more deeply in a particular NoSQL database type, then do that, because this course is designed to cover more broadly the entire ecosystem so that you can select the appropriate products of interest. And the products have become more complex. And as I said originally, each product has its own method of interaction, and you need to commit some time to it. So now that means even more time to get the proper value out of it. Also, there are now abstraction layers, ORM-like or object relation model layers that sit on top. Some of them, for example, are designed for specific solutions. Amplify from AWS, which is designed to get you to value in a mobile app faster, abstracts away the underlying NoSQL database. And again, for the scope of the course, I won't be able to cover all those. I'll just mention when you should look at them, but they can get you to value faster. Tools and enterprise support also are something worth looking at. So I'm not saying that it's no longer interesting to look at open source NoSQL databases. What I am saying is, from a practical point, there is an ecosystem built up around NoSQL now that makes it more enterprise-like. That is something you should evaluate when you're considering your use of NoSQL for your solution. We're going to consider this quote. Memory storage is number one. The Redis data set, composed of defined key value pairs, is primarily stored in the computer's memory. This is from the Redis, which is the key value NoSQL database manifesto. So what would you use a key value NoSQL database for? You would store huge lists. So key value stores, such as Redis, there are others. I've worked with one called Aerospike, for example. They can store huge lists. And as the quote mentioned, the idea is in memory. So very, very fast. These lists, which are sometimes called dictionaries, are stored in memory by default, but can be configured to be persistent on disk. Of course, there's going to be a very significant performance cost to this. So very often, key value in memory databases are used for what is called hot data, or data that needs to be accessed very frequently in applications. Lookups, for example. So it's also used for application and requirements, which include caching. So in the past, this would have been an object in your application, a hash table or something. But if there's too much data in it, then you can actually use a database, a NoSQL database. They're extremely fast and easily scalable. And as you might guess, based on our previous discussion of CAP, they are not by default transactionally consistent, which is important to understand. Let's look at a Redis data structure so that we can understand what a key value database looks like in terms of data storage. It's just as the picture shows. There's a key and a value. Now, these different types of data that are shown are different types of values that can be stored. These are data types in Redis, strings, bitmaps, so on and so forth. And it's really important to understand these are very different, especially if you come from a relational background, from relational data types. There's no such thing as hyperlog logs, for example, by default in SQL Server, Oracle, so on and so forth. So you want to understand the data typing in your particular NoSQL system, not so much for the purposes of write, because remember, NoSQL databases are schema on read, more so on read for optimizations such as partitioning, indexing, so on and so forth. Here are some examples of key value NoSQL databases. There are many more than this, but these are ones that I've used in production. So Redis or Redis Labs, Memcached, Google Cloud Platform Cloud Memory Store for Redis, AWS Elasticache for Redis or Memcached. Now, I want to give you the 1, 2, 3 of NoSQL. And what I mean by this is when you're thinking about whether or not you're going to use a particular NoSQL database, in this case, a key value NoSQL database, you generally will have 3 ways you can implement it. You can implement pure open source, so there'll be no licensing cost. You can implement enterprise in many cases. Many of these open source projects have been turned into commercial entities. For that, you will be paying a license fee, and that can be on-prem or in the cloud. Or you can implement what I call a cloud native, if it's available. And in this case, that's GCP Cloud Memory Store for Redis. You see Redis and Redis Labs. So Redis itself is free, requires servers, and there are no tools or support. You know, again, it's kind of illusory sometimes about the low cost. The cost that you're going to pay is you set it up, you maintain it, you tune it, so on and so forth. Redis Labs is the Enterprise Edition, requires servers, and they provide support, tools, training, so on and so forth. This can be on-prem or cloud. And the Cloud Native, in our case for GCP, there's one for Amazon as well, is a managed service, and it gives you support and tools that are integrated into the GCP ecosystem, in our case, Stackdriver, which this option 3 is relatively new for many of these services over the past 12 to 24 months. And I'm finding is a really good option to consider for my enterprise customers. So comparing options 2 and 3 is a typical sort of scenario that we work with. In this course, I'm going to be showing you most of the time the cloud-based solutions, because those are the ones that I'm generally going to be using with my customers. So to that end, we'll see some demos coming up here on Cloud Memory Store and then the Amazon solution. To work with the Redis key value NoSQL store on the Google Cloud Platform, you have a number of choices. And what I've done is I've set up using Cloud Memory Store here, an instance for us to work with. It's pretty fast to set up. And if you want to try this out and you don't have a Google Cloud account, just set a new one up. You get $300 in free credit. And then you'll have to enable the API on just a click of a blue button. It took about 5 minutes to set it up. I'm going to demonstrate what this looks like and how you would connect to it. So inside of here, I have already set one up, but you would just generally click this instance. And you can see Cloud Memory Store is a fully managed Redis service for a Google Cloud Platform. And like other services, it's managed. It tells you how much it would be per month. You set the instance information, the basic or the standard. Notice you're not going with high availability here on the standard. If I switch that, there's the price difference. Here you set the location, you set the capacity. Notice if I put this up, then that just goes up by a factor of, the appropriate amount there. And then it shows the estimated network throughput for your capacity planning. You can set the Redis version 3, 2, and 4 are supported as of this recording. If you have a custom configuration, you can add that. You set up your networking information, and then you can set up your instance IP address range. Now, once you set that up, what you get is you get an integrated managed Redis cluster, and you can see you get some simple monitoring here. You can see the instance properties, connection properties, and the authorized network. Now, if you wanted to, you could simply take Redis backup file, which is called a dump file, and you could import it. So if you had like an on-prem Redis or, coming from another cloud or something, you could just import that and then bring that in. Now, as is typical with many services in the Google Cloud Web UI, there is no capacity here to insert data, query data, and this is sort of typical for Google. Oftentimes they don't make functionality available in the web UI. If you wanted to do further probing or interaction using a Google client, you would use this Cloud Shell, and that would open up a VM. And then you can use their scripting, which is the gcloud command, and you can interact that way. So in their documentation, you can then just type gcloud, and this is a separate VM, so client, if you will. Now, that's one way to do it. Another way to do it is to, let me close this out. Simplest possible way here from their documentation is to set up another virtual machine on your Google infrastructure and to use the telnet, kind of old school methodology of just basically pinging your instance. So you can see first you just install it, and then you get the instance IP address and you just connect to the port. And then once you connect to the port, then you enter some Redis commands. Now, when you interact with Redis, it's a set and a get. Again, like I was saying, this is not the world of SQL, it's NoSQL. So set hello world, and then you get hello. This is sort of the simplest possible way. So I have this set up, and the IP is here, and then I have the compute engine instance set up. So let me SSH to that. And again, in the Google world, if you're new to this, unlike some of the other worlds, Amazon notably, you have this integrated terminal. I think maybe Amazon actually has this now, but it's relatively new. Google has always had it. So you get automatic key transfer, and here you're into the terminal. So let's go ahead and get apt-get. So we can just copy this, and I misspoke there. Let's get telnet using apt-get. Okay, so there it is. And I did install it once. I'm kind of just doing this for illustration purposes. So let's get a text editor here and fix this. So now I will get the instance IP address and telnet to it. So the instance IP address is here, and then I just offline, I use a text editor to just set this command up. And there's our connection, and we are connected. And so now we can type ping, and we get back pong, and we can type set hello world, and we get back okay, and then we can get hello. Now, if we wanted to, at this point, we've put some data into our Redis instance, so we could export this as a backup file, and we can move this around. Now, when we're working with this instance, we can see that we have a certain capacity set up here, and we have the basic monitoring inside of here, but we can integrate with the Google monitoring, Stackdriver monitoring. This instance lives within the Google network. So there are other ways to work with Redis in Google. For example, if you just type Redis, you can see that we have some click to deploy. And this is open source Redis that has been set up and can either be run on containers or it can be run on virtual machines. So when you are working with Redis on the Google Cloud Platform, I recommend you take a look at Memory Store, or basically you just type in here because there are more solutions coming up. You can see Redis Enterprise from Redis Labs is available, and they've configured it. So it's really quick and easy to set up a key value store. Now, I did kind of skip over the client. Redis itself has a client, a CLI that you would install. I just kind of did a hello world. So you'd want to look into the documentation here, export and import data, and then set up the Redis client or the API, which is more typical, is that you would be programming against this in your application. Now, to work with managed NoSQL key value Redis on Amazon, I'm in the Amazon console here. And again, like with Google, you can just set up a trial account. And notice when you type Redis, you get their managed service, which is called Elasticache. Now, unlike Google service, this took a little longer when I set this up. So it took about 5-10 minutes. So Google's took less than 5. So I'm going to start it and probably pause the video. So if I click Get Started Now, you can see I have two options. I have Redis or I have a Memcached. So again, this shows really an example of a cloud managed version of an open source key value NoSQL store for hot in-memory data. So you can see Elasticache for Redis offers multi-availability zone with auto failover and enhanced robustness. So it's optimized. So it's often used for caching, message broker, and you can set up cluster mode. So you would just fill in this. And of course, if you were doing this in production, you would script this and you would capture your script in your source control. This is really just for demonstration. NoSQL course. And you can see the engine compatibility. They have a little bit more variety here. Google, you remember, had only less versions. The port, parameter group, number of replicas, and the node type. So you can see this is set up by default for a pretty big size. And the idea is, again, that this is going to be a massive data storage. Now, if you're using a brand new Amazon account, you might have to make sure that you can get this number of instance. These are EC2 virtual machine instances, because if you are using this instance size for something else, Amazon purposely limits, as does Google and Azure, everybody, how many of big instances you can get. It's basically for your own protection. So if somebody doesn't get in there and spin up too many instances and run up charges. So you can see here you've got advanced settings, multi-AZ, subnet group. We're going to create new, and we're going to call this a demo, Redis, NoSQL course. Here's your VPC, and you need some subnets. So, because you're going to have high availability, you can have encryption. And with Google, you can have this stuff as well. It's just not all these parameters are exposed via the web UI. This is, again, kind of a vendor difference. Google, you can get them via G-Cloud. It's still kind of the same capabilities. It's just differently how you get them. Here you can import, again, a dump file, set up automatic backups. This is the managed aspect, and have the maintenance, either by no preference or a maintenance window. So you fill this out, and then you just click Create, and then basically you wait. So then you can access your Redis cluster. Now, while we're waiting for this, just a couple more things to consider in the Amazon ecosystem. Kind of like Google, you can have Redis that is not Amazon optimized, if you will, or managed by going over to their marketplace. You might remember we went to Google's marketplace and we looked at their Redis created implementations. So the difference is, Redis is creating those and optimizing them for the vendor rather than the vendor creating them. And in real production situations, it is interesting to see who does a better job. So I've actually load tested at scale, for example, an Amazon configuration for Amazon versus a Redis configuration on Amazon. So you can see over here, if I search Redis in the marketplace, these are images basically. Well, we have a number of different images that have been made available, some by Redis Enterprise, which is the commercial side of Redis, and some by, different vendors that use Redis in their product. So again, lots to choose from. When you're just getting started, I really recommend, and that's why I'm showing this first, to use the vendor's implementation if you're going up on the cloud. Of course, with this, you would also have to create a full client. And so you'd get an EC2 instance, and then you would install the Redis binaries for the Redis client, and then you could interact from a command line. Or if you want to, you can go directly to the API. You can see in the menu options, we have Redis Memcached, which is the other engine, service updates, reserve nodes. This is a way to save money, basically in production, backups, parameter groups, subnets, events, And then we do have a client that we can look at here. I actually think I'll just pause the video and then come back to this when it's complete so I can show you what it looks like. Okay, you can see in the Amazon console that my Elasticache Redis cluster is now available. So inside of here, it's Redis. There's one shard, 3 nodes. Here's the node type. Status is available. It's up to date. It's not encrypted. And if I click here, you can see more information about it, as well as I have the ability to perform the actions that are available: backup, modify, delete. I can migrate data from the endpoint. It's really important to understand where the endpoint is. So here it is. And if I were going to then work with this, I would use this endpoint from my separate client machine, which would probably be a EC2 instance here. And importantly, I would have to set up the appropriate security rules. When you are working with server-based instances on the cloud, you have to set up your security rules. And in Amazon, of course, that's in your security group to allow traffic from this port 6379. Like in Google, if we click in here, we can see that we have some information about the nodes. And if we click the node here, we can see that we have some basic metrics shown here, CloudWatch metrics in the case of Amazon, for each node. So CPU utilization and swap usage, and then which is memory, network, so on and so forth. So something specific to Redis. So evictions, reclaimed items. This is to do with memory usage, because of course the idea here is that you're going to have all of your data in memory and you're going to size your cluster appropriately. So you can see at the node level, if we wanted to add a node, we can do that here. Now, of course, as with Google, when we're in the Amazon world, we use the console for learning, but for any sort of production situation, we should be using the AWS CLI to script any changes to our cluster. We should also capture our cluster configuration and put that into our source control for any sort of production situation. So if we wanted to then get rid of this, then we would click here, and then we would simply click on delete. And then it would, by default, make a final backup. We don't need one in this case. And we're going to say delete. And then I will also remind you that if in an earlier movie you created a GCP memory store instance and an EC2 client, you're going to want to shut those off as well if you're done working with them at this point. So now that we've seen a cloud key value NoSQL database, namely Redis, in action, let's talk about where you would use this in the real world by example with an architecture. So for my architectural examples in this course, I've tried to use reference architectures published by Amazon or Google rather than ones that I created myself for clients. First, because my client ones are proprietary. And second, one of the nice features of some of these architectures, mostly the Amazon ones, is that they include a CloudFormation template. So I've put the link here, and if you want to actually just click that template, it will build the architecture so you can actually explore it in more detail. However, do be aware there can be some substantial cloud service charges if you choose to do that. So anyway, this first architecture is a scalable chat app, and it uses a PubSub or publisher subscriber pattern. And I picked it. I thought it was interesting because this is similar to a situation I had with a real client where the natural thing is to use PubSub because it's a service. So I thought it was interesting because it showed an alternative to using PubSub with key value NoSQL implementation. So Elasticache, it has a Node.js front end and it has a Node.js WebSockets back end. And like I said, the link is to the Amazon blog post that explains the connection through WebSockets, because I'm sure some of you people listening will want to know about that, even though it's not directly related to the NoSQL choice. It's still interesting. And you can also, like I said, using CloudFormation, implement the architecture. So here's what it looks like. And you can see highlighted. It's pretty simple, which I like. Simple is hard, but generally good. So you've got chat clients going to the Amazon cloud, and inside of a VPC, inside of Elastic Beanstalk, which is websites as a service, if you will, you're running a Node.js application. So those are the chat servers, the front end, and they have an app load balancer, an ALB on the front. And they're in two separate security groups, which is a best practice. And then you can see in a separate security group, you have Amazon Elasticache for Redis. Now, I will mention the security here because, again, this is an area whenever you have data that people tend to neglect. So when you have server-based NoSQL solutions on the cloud, then you have to configure the security boundaries yourself. So the security groups, if you will, which are the virtual firewalls. When you have serverless, then it's role-based security. And this pattern is not, specific to NoSQL. It's just something I don't hear mentioned often enough. So cloud server-based requires configuration of security groups and testing to make sure the proper ports are open. In the case of Redis, of course, it's 6379 by default. In the case of serverless, which we'll see in some other NoSQL solutions, that's proper role-based management. So you can see here the chat app uses Elasticache for Redis because it's a great solution to keep the chat information very, very available and fast in memory and very scalable. So it's a simple architecture that's, not, I wouldn't say production ready, but it's a great starting point for a proof of concept. And it's sort of an elegant use of a key value store. So if you want to try it out, you can go to the link. Otherwise, this is showing this architecture. In this next section, let's consider this quote. Data is the new science. Big data holds the answers. It's from Angela Ahrendts from Apple. In this section, we're going to take a look at capturing customer events with NoSQL. A typical type of database that we would select for this type of scenario would be a column store. An example of this is Cassandra, which is open source, and it could store customer events. This is that behavioral data that we were talking about earlier in this course. If you're in a store, where did you walk in the store? What did you look at? What did you pick up? Not necessarily what did you buy. So these behavioral events are stored in what are called irregular or jagged or sparse tabular structures. Sometimes they're called matrices because they're multidimensional. And they're used to store ragged data sets. They can be used for just retrieving individual events or for retrieving aggregates. It depends on the type of NoSQL store that you select here. And they can be extremely fast, either for these individual or aggregate queries, and they're going to be scalable. Of course, they are not going to be transactionally consistent by default, or even sometimes it's not even possible to make these stores transactionally consistent. So it's really important to understand the differences between this and using a relational database, for example. It's important to consider how the data is stored in a column store. In a relational database, data is stored in a record-oriented manner in relational tables, so customers and their orders, for example. In a column store, the data is stored in column families in a column-oriented structure. And this diagram is from a representation of a service called Dremel that was made by Google that is the basis for a number of their commercial products. But it really represents visually the difference in the storage of a column store and a row store. So some examples of columnar NoSQL databases are, as I mentioned, Cassandra, which was developed at Facebook and then open sourced and took a kind of familiar route, kind of like Redis and Mongo and some of the other big open source NoSQL databases. There's a free version and there's a commercial version. Google Bigtable, which is sometimes called an events store, is Google's representation of a columnar NoSQL database service on their GCP platform. Also, interestingly, you may remember when we talked about the CAP theorem earlier in this course, their product GCP Spanner is transactionally consistent while being highly available and partitionable. And it is actually a physical layer that was built on top of Bigtable. I put a link to that white paper in this slide because I thought it was an interesting read. Also, and somewhat surprisingly, another columnar as a basis service is GCP BigQuery. This is an aggregation store rather than an event store, so replacement data warehouse, and much, much more. Again, when we're looking at how we're going to select our column store NoSQL, we have a similar set of three choices as we've presented in previous types. One is pure open source, Cassandra, so it's free, it requires servers, and there's no supporter tools, so it has that cost structure. If you want to capture cloud events, then the GCP Big Table service is an optional columnar choice. It's a managed service. Notably, it's serverless, and Google supplies support and tools. And for cloud warehousing, GCP BigQuery is a managed, built on a column store, but the implementation is a bit different, and it's serverless. Both Bigtable and BigQuery I would consider quite advanced products. I've used them since before inception. Being Google Insider, I had the opportunity to try them out and been really excited about them. I mean, you have to remember that the basis for this entire industry was generated in companies like Google, so it's not surprising that their services are some of the most performant and provide some of the best value at high scale. And of course, for the cloud warehouse, you'll have support and tools as well. So to look at NoSQL column stores, let's first look on AWS, and in the search box here, we'll type Cassandra, and relatively new is their managed Cassandra service. So let's take a look at that. So this is less than 12 months old, and the idea here is that Amazon's providing you with their version of optimized Cassandra. And you can see here that you have a Cassandra application, and then you have your managed service. So if we click Get Started, it's really kind of great, and I wish all NoSQL databases had this, because I know years ago when I was exploring all of them, all the different terms and ways of storing and ways of querying are, as I was mentioning, unique to the NoSQL database type. And I love this quick start. It's really well done. So good job, Amazon. So you can see that you have a couple steps to set this up. So you would first create what's called a key space, and they define what it is in case you're new to this. So it's a way to group related tables, and they talk about using multiple availability zones for high availability. And then here is the Cassandra query language, which would create this empty sample key space. And you can see here it is, and we just click Create Key Space. Then the next step is we want to create a table in the key space. So it tells you here that tables are the primary data structures, and they're organized into rows and columns. Of course, they're going to be a column store underneath the hood. That's the point here. So you can see here is the CQL to create a table called tutorial table in our tutorial key space. And it has these values in it: name, email, age, and primary key is the email. And now the table has been created. So the next step is to populate the table with data. And notice here we're going to insert a row. So we're going to insert values into this particular table. And the values are shown here. And then we're going to query our data and run the command. We have a query editor, and we can see there's our record. But of course, under the hood, although this looks quite relational, remember it's a column store. So in this case, the actual information is stored in a JSON format. So I love the ability to quickly get going here. If you're new to working with Cassandra, the integration is really nice. I mean, if you contrast this with what you would have to do to go to the Cassandra site, get the binaries, download them, set up a client, so on and so forth. I mean, you're really saving a lot of time. Now, once you set this up, then notice we have an integration with CloudWatch, which again is another reason to use vendor optimized version rather than open source version. And then here are your key spaces, and you can see it's the replication strategy inside of here. And then here's your table. And you can see the schema of the table. And if you wanted to query, we have included query editor in the web UI, which again is really sort of nice to work with. So as with the previous example, we could use in the Amazon Marketplace a Cassandra image that was optimized by the Cassandra committers. But my experience would be that when the vendor provides you with a managed service, particularly if you're new to it, it's a great way to get started. Now, in the Google world for columnar NoSQL databases, we have Bigtable. And I went ahead and created an instance already. Remember, this is serverless, so I'll show you what you would need to fill out. The instance name, the ID, the type, production 3 nodes or dev, whether it's SSD or HDD drives, cluster location, number of nodes, performance. Here they show the performance. And then again, Google will give you a cost estimate. So I'll just put in an example here. And once I select a region and a zone and a number of nodes, it gives a cost estimate. Notice if I take the storage size up, of course, the cost estimate, well, first it's telling me I don't have enough space for this. So the cost estimate will change, which I just really like this. I think it's a great feature. And then it gives you the ability to put in a replicated cluster as well. As is typical, this creates pretty quickly. So I did create an instance already, and you can see here that it has 3 nodes. It gives me a quick view of the storage utilization. Now, a sort of vendor difference between Google and Amazon is, and I mentioned this earlier, but this does come into play in the NoSQL database world quite frequently for some reason. As Amazon's really good at setting up their UI so you can just click and get started, Google doesn't really do that as often. And this is an example here in Big Tables. So inside of here, even though you can create the instance, you can't really do anything in terms of tables or data inside of here. You have to use the gcloud command. Now, what I did, because I found their documentation to be a bit hard to go through, is I actually wrote a simpler version. So I have a separate course called GCP Essentials that goes over basically almost all Google services. And in here, I have sections. And the big table one, I actually always use it myself. So you can see that this is from their documentation, and the gcloud command uses the Cloud Big Table tool. And so you may remember that to use gcloud, you can just open up a terminal in the bottom, and I've already done that here. I'm just going to bring this up. And you can see that I ran these commands, and then I configured this cbttrc file, and then I listed the clusters. So you can see in here, I had to put the instance name, instances list, and then here is the name of my cluster, demo NoSQL. There it is. And then to create a table, even though in the UI there are tables, you can only look at them. You can't create them from here. So you have to use either the SDK with, Node or something, or you can use this gcloud commands. So the way that works is create table, but in my case, I got an error that I was missing the instance. So I had to put the instance, and the correct syntax is here. So you have to say instance demo NoSQL in my case, and create table my table. And then when we list them, you have to put the instance. It wasn't picking up the instance for some reason. So you can see there's my table. And then you create a column family. So we created a column family here called column family 1. And then this is how you put data in. So set for my table for column family 1, a test value. And again, I have all this here in terms of a script on GitHub, and there's the URL for GitHub, so that you can add a column family, you can view it, you can put a test value, and you can read it. So once you put it in, then here we're reading my table, and you can see, again, it's in JSON. So it's just a little bit different in the way that you interact with it. You can have the monitoring, just like you have in Amazon. So it's a similar type of integrated monitoring. Also, they have a key visualizer, which is kind of interesting. This is only significant if you have a whole bunch of keys. It basically is a heat map, and it shows you where your data is. So it's kind of a useful thing. So this is an integrated, unique to Google implementation. And this is something they used internally, and it's a hugely scalable event store called Bigtable. Now, this next NoSQL service isn't really NoSQL, so it's a little bit tricky. The underlying storage is NoSQL, but the query layer is actually SQL. But I'm getting ahead of myself. It's called Google BigQuery. So in order to use this in your Google Cloud account, if you go to the Marketplace and Data Sets, and that's just off the menu over here, and then I'm just going to search for some data. So I'm going to pick storm data. This is public data. And if you click that, it'll say View Dataset. Once you click View Dataset, it'll take that dataset and it'll make it available in the BigQuery service. The service is so advanced, it's really kind of almost like magic. So once you click that, which I already did, you can see here's the BigQuery public data, and then you can see all the different data here, including the new NOAA Storm Prediction Center data. So let's see what it's actually called. NOAA. So down here, NOAA, Preliminary Severe Storms. So that's going to be here. So this is all public data that you can access. And this really goes back to sort of the beginning of NoSQL and being started by Google. So this service is the commercialization of a set of services that have been used inside of Google for years and years and years. And the service is actually not new. It's been out since 2011. And when it was released, it was so revolutionary. People actually didn't understand it. They didn't get it. They just didn't believe it, basically. So what is this? Well, the underlying storage is a column store, but you don't see it or care about it because it's serverless. And really the brilliance of the service is that the column store is designed for aggregation, so the sort of the classic data warehousing of events. However, the top query layer, unlike everything else I'm going to show in this course, is actually SQL. So this is NoSQL SQL, which is a little bit crazy, but I think it's the most advanced, most usable, and it's something I use with almost every customer. Why? Because people want to use SQL. They know SQL, and they want it to be scalable, and they want it to be partitionable, and they don't want to deal with managing servers, and that's really what you get with this. So you can see inside of here, I created a query. So I looked at the data itself, which has these hail reports, tornado reports, and wind reports. And I just selected some of the data. And before I clicked run, it told me how much data would be processed. Why? And again, I think this is the front end of the NoSQL movement. Actually, it sort of comes back around to SQL. The idea is you pay only for the amount of data scanned. You don't pay for servers. You don't pay for licenses. You don't pay for hardware. You pay for query as a service, if you will. And you can see once you run this, you get the result. Now this is going to be cached because I already ran it once. And of course it's JSON under the hood because we're in a column store situation. Also, you can look here at the execution details, which you might want to when you're running massive queries to see how you might want to optimize this. And again, this course really isn't getting into the depths of optimization because each of these products could be its own course. But I will tell you that it is extremely important that you understand how to optimize. This is one where I've actually done quite a bit of production work. So you might do something like partitioning the underlying files, compressing the underlying files, changing them to a different format because it was more efficient in terms of columnar reads. So the thing that is fascinating about this is it looks like a SQL database, but it is as far away from a SQL database as can possibly be. It's serverless and massively scalable and a column store. And if you don't believe me looking at this, I highly encourage you to read this white paper, which talks about the underlying column store, which is called Dremel. And I know when it first came out, I really wanted to understand how Google was able to do it. And I think in terms of what's happening with NoSQL and the possibility of NoSQL, frankly, you always want to look to the leadership of companies at the scale of Google. I mean, they don't do all of the work, but they've done quite a lot of the work. So if you read in here, it talks about how this paradigm of distributed compute on a column store was created. And there's the actual diagram that I used. And what are the mathematics behind this, how this actually processes data. You can see it's a nested columnar store. Also, this is really useful if you're going to work with this service at scale, because if you understand the underlying storage, then you can understand how to properly optimize so that this amount of data scanned is the least possible so you can provide the best value for your customers or for your business if you're working directly for a company. So again, this is one that I would say you're probably surprised is in this course, but I think it's kind of the future because the SQL query layer is what people want. It's not by accident that a lot of these something QL query languages look like SQL. You might have noticed that Cassandra in the previous movie looked like SQL. It's not, though. This is actual SQL. which is really kind of interesting. So it's an evaluative filter when you're looking at NoSQL solutions. What is the query layer language like? How usable is it? And frankly, the closer it is to ANSI SQL, probably the higher value it's going to provide more quickly to you. So now let's look at applying this cloud columnar NoSQL services to an architecture. In this case, we're going to be building a scalable ad tech application, and we want to use column stores for both events, which is individual queries, and analytics patterns, which is aggregate queries. Be a pub sub on the front end, which is really typical for events or event streams, because usually events come in streams. Because we're going to actually be working with the Google ecosystem here, we're going to use their middleware product called Dataflow, which is a implementation of open source Apache Beam, which is a distributed data processing platform that many people at Google and others worked with. And importantly, we're going to use a NoSQL column store multi-service backend. So here's Google's reference architecture for this type of solution. You can see the information is being collected in a modern way with multiple different types of systems collecting the customer events. So we have beacons. So these could be in, for example, a retail store, or they could be at an event. We have back office business systems, and we have mobile devices that in this case are getting push notifications when certain thresholds are met. So within Google Cloud, we have PubSub that the events are coming in on, and then our processing is happening on the Dataflow platform. Messaging is going to PubSub and the notifications through App Engine, which is the serverless web hosting set of services on GCP. Germane to our discussion, though, is the backend. And you'll see that we have the event and analytic pattern that I've built many times for customers. This is a really common pattern. And I particularly enjoy using Google Cloud for this pattern because, as I've been saying, their services here are really very advanced in terms of the value that they provide. So Cloud Bigtable is your event store, your scalable event store. And no, it is serverless as well. And BigQuery is your analytics store. So you have the SQL layer built on top of the column store, and that provides the data warehouse functionality in a serverless fashion. We'll start a discussion of document NoSQL databases with a quote from Werner Vogels, the CTO of Amazon. He said, "It all started in 2004 when Amazon was running Oracle's Enterprise Edition with clustering and replication. We had an advanced team of database administrators and access to top experts within Oracle. We were pushing the limits of what was a leading commercial database at the time, and were unable to sustain the availability, scalability, and performance needed that our growing Amazon business demanded." I think that quote is a very useful introduction to document NoSQL databases. Google wasn't the only player who created the basis for what has become a type of NoSQL database. In other words, the column stores we just looked at. The dominant document store was created out of needs of Amazon. So we're going to take a look at storing customer activity with NoSQL using document stores such as MongoDB and DynamoDB, which is Amazon, to store customer activity. These stores are going to store behavioral events and documents, and they're going to be stored in irregularly shaped tables. These are also called ragged data sets. An example of this is a customer may perform behavior A, B, and C in one case, and B, C, and D in another case. As with other NoSQL structures, these document databases are extremely fast for querying and easily scalable, and they are not by default transactionally consistent. To visualize what this information would look like, here's an example from the MongoDB documentation. Our document store would store information with a key and a value, but the value would be a document. Those documents generally take formats that are those such as JSON, which stands for JavaScript Object Notation, as shown here, BSON, which is Binary Object Notation, which is serialized, or other forms such as XML. Examples of document NoSQL databases are MongoDB, which is open source, or there's a commercial version, AWS DynamoDB, which supports both key values and documents, and newly released AWS DocumentDB, which is MongoDB compatible. Again, as with other categories of NoSQL databases, we have basically three types of implementation choices around document NoSQL databases. We could use pure open source, such as MongoDB. Licensing would be free. We would have to set up our servers. There would be no support or tools, so those costs would be substantial. We could use cloud document database, such as AWS DocumentDB, which is a managed service. It does require servers. Interestingly, it's MongoDB compatible, and Amazon does supply support and tools. Or we could use a multi-purpose NoSQL database. And this is the first of a couple of examples that we'll see in this course of what I call the more evolved or the more useful NoSQL databases, in that DynamoDB, although it originated as a key value store, it has evolved to have full support for documents as well. And I would argue that in many cases, having the capabilities to support two types of NoSQL implementations increases the usability and the value to customers. This is a managed service. It's serverless, which is another huge plus point, and you get Amazon support and tools. And we'll take a look at all three of these in subsequent movies. Let's take a look at MongoDB on GCP. In order to do that, as with previous examples, we'll just go into the search box here in the web UI and type Mongo. And you'll see that we have a number of choices. And as with Redis, when we looked at that in a previous movie, you can see here that we have Google-supported deployments through the Google Marketplace. And I've gone ahead and set one of these up because it takes a few minutes. You'll notice here that some of them are administered by Google and some of them are administered by Mongo. So it's a similar type of decision vector as what we've seen. Now, over in the Deployments Manager, what I have done is I have selected to deploy MongoDB, created by Google Click to Deploy. And what we're looking at here is a templating solution. So deployment in Google is similar to a CloudFormation template in Amazon, in that it's an end-to-end solution and it incorporates all the various objects that you would need. And you can see here that I've configured this and it has set up everything that I would need. Actually, what I think I'm going to do, just to show you what is configurable here, is I'll just open this up and see you get a launch on Compute Engine. It shows you I have a deployment of this, how much it would cost. It's on VMs. Other options would be on containers, for example. It's a database. And here's pricing information. Really helps you get up and going much more quickly than just installing this on a Google VM, for example. And then if you click Launch on Compute Engine, what you then are presented with is, in this case, a nice graphic, which shows you what you're going to get. These are Compute Engine instances, primary, secondary, and an arbiter in this case. Now, one thing I would caution you, on my trial account, I had to set the server tier instance count to 1. Otherwise, I exceeded the number of CPUs that were available. And again, this is a throttling that's put on free tier accounts to avoid fraud, basically, and unexpected charges. But other than that, I could just accept all the defaults. And then I just clicked deploy. And it took about 10 minutes to deploy. So once it's deployed, what you have is you have this, which shows the deployment, and it gives you more information. Again, this really helps you get up and running quickly. So it's a tip when you're evaluating NoSQL, rather than, going through the pain of installing this manually on either a local virtual machine or a cloud-based virtual machine. Using the marketplace is really, I think, very important when you're evaluating. So you can see once it's set up, then how do you connect to it? As is sort of typical in the Google world, you are going to use the shell. So here it tells you to use this gcloud command and to connect. So I'm going to copy this command. I'm going to go over back here and go back home, open up the shell. I'm going to make it a little bit bigger so you can see it better. And then you can see that I'm SSHing to my particular implementation. And then once I'm in, what I can then do is I can work with the Mongo shell. And I start the Mongo shell with the word Mongo. This is the Mongo client. And again, just to be clear on this Google Cloud Shell is a separate VM, so it's a client machine. It's not the actual cluster. And now we're in the Mongo prompt. Now here, if you're unfamiliar, I just opened the Mongo documentation, and you can see that we're in the page here of the Mongo shell. So if I scroll down to work with the Mongo shell, we are going to display the database that we're using. So we're going to go over here and just type DB, and we're in the test database. And then we're going to insert a value into the test database. Notice the syntax here is collections. So it almost looks like a key value pair. It's really simple. Obviously, this is designed for nested documents, so it could be a lot more complex than X:1, but just to get the idea. And then we'll just paste this here, and you can see that the acknowledgement is true and it's inserted and gives you an object ID. So again, if you're new to Mongo, this is a great way to start working with the types of data. You can go through here and just use this quick client. I really like the way that this works. The other thing I like about the deployments when evaluating NoSQL solutions on the cloud is that not only can you set them up really easily, but I'll show you here. If I go in here and I click delete, it's going to delete all of the objects that were created with this. It's a transactional deployment. It's very much like CloudFormation and Amazon Stacks and Templates, Google Cloud Platform deployments. And you get them out of the Google Cloud Marketplace. So the marketplace is right here. But I generally just search because the search works pretty well inside of here. It's a Google product, right? So I'm going to go ahead and just go back here, and then I'm going to go and just delete my deployment because I'm done with it. So now we're going to take a look at Mongo on AWS or document database. So if I type Mongo, again, I really like the clever search capability here. Remember when we typed Cassandra, we got Elasticache. So Amazon's doing a good job with SEO here. So we have a relatively new offering called DocumentDB, and DocumentDB is a MongoDB compatible database service. Now, the cynical among us would say that Amazon is simply trying to basically eliminate all their competitors by creating alternative solutions. And I think you wouldn't be wrong in this particular case, because rather than optimize MongoDB for AWS, Amazon has gone the route of creating their own Mongo compatible version, so direct competition. So it's called DocumentDB. I've already made one here, but I'm going to go ahead and click create and show you what this would look like. It's very much in the vein of the managed NoSQL databases. So you create a cluster, you set up the instance class, the number of instances. You have to set up the authentication, the username, the password. It tells you how much it will cost. And then you create the cluster. And this takes, again, about 5-10 minutes. It is server-based. And you have the ability to manage the instances and make snapshots as well. So I've set this up, and you can see once you do that, then it gives you the ability to connect. You can connect as a Mongo client, and you can see here, this is the command that you would use from your separate, in this case, EC2 instance to connect. You also could connect with an application, which would be a typical sort of production use case of this. You can see information about your particular cluster, including the endpoints, information about the backups, so on and so forth. Now, I will leave the client configuration as an exercise for you since we just did it in Google. You can see here is the directions. It's really very similar. You would have to spin up an EC2 instance, and then you would install the Mongo shell. And then once you installed the Mongo shell, and then you would use that command that I pointed out there to connect from the client. And then you would be able to use the Mongo shell as we did previous movie using the Google instance of this. And you can see here's an example using the Mongo shell of inserting a more typical size document. You might remember from the previous movie, we just said X is 1, but this is sort of a more typical ragged and nested JSON document. So in this case, DB inventory insert, and here's the document. And then here we're calling a find command. And if we wanted to update, we would update here. And then we could delete, which is called remove in this syntax. Now, one of the reasons I am showing you this page is if this syntax just seems really strange to you, if you come from a SQL background, well, that kind of is the point. You know, I've been talking about the challenge of learning the particular data access language for the particular type of NoSQL implementation that you select. And it, you know, again, I keep saying because it's non-trivial. I've seen many a dev group just really not consider how long it's going to take them to figure out how to use this syntax if they have a relational background. Now, not every dev group does. Some come, you know, directly out of maybe university and they've never actually worked with relational databases, so they don't have to unlearn it. But in any case, it's not a like for like, and that's really, really important. So when you are going through and setting up, you're going to want to always get to the point of creating the cluster, creating the database, and then doing a hello world, which is inserting some data, maybe updating it and deleting it. So you can at least get that level of functionality to understand what it's like to work with the NoSQL product. And again, as an aside, I have to tell you, and having worked with, you know, tens, maybe even 50 different NoSQL databases, sometimes just doing that can take too much time, which will tell you quite a lot about the functionality. One of the reasons I'm focusing on cloud-based NoSQL databases is they're faster. They're faster to set up. They're faster to optimize. And the reason you use NoSQL is to get value faster. Next up in document and key value NoSQL databases is probably the most widely used now NoSQL database in the world, and that's DynamoDB. As I said in my introduction to this section, through the quote with Werner Vogels, the Amazon CTO, Amazon productized this technology that they used to solve their own business problem. And I think because of this, this service has been quite revolutionary and highly usable since its initial release. And Amazon really just continually improves it. It's kind of, to me, the standard for cloud NoSQL databases. I always look to see what is going on with DynamoDB because as great as it is, Amazon continues to make it even better. So let's get into it, and I'll point out some of the aspects, the core aspects, and some of the interesting new features. So like anything else in Amazon, we click the blue button, and it's tables as a service. So we're going to call this table customers, and let's create a partition key. Now, the selection of partition key in production size loads is really important. The data needs to be distributed appropriately. So again, this is part of that learn how to use the product based on what the vendor tells you. And you can add a sort key. Notice the table settings by default have no secondary indexes. There's a provision capacity set to 5 reads and 5 writes. It's not 5 individual rows or columns. It's vendor determined capacity. It has alarms set at 80% upper threshold and an encryption at rest with default encryption type. And I don't have the required role to enable auto-scaling by default. I can also now add tags. Tagging, of course, is important to identify resources in the Amazon ecosystem, so key value pairs. And I'm going to click Create. So the creation is going to be almost instantaneous. And the UI here is great. It's really easy to use. Of course, in any production situation, you're going to use the AWS CLI and script any of the work with the tables and check that into your source control. It's really, really great for discovery here. So you can see that we have the ability to associate DynamoDB tables with streams. Well, that's pretty logical since eventing and event streams is increasingly a customer request. Here we have table details, and notice we have the ability to have a point-in-time recovery. This is a relatively new feature. We can manage our encryption. We can use our own keys. This is very new. CloudWatch Contributor Insights, it's in preview. So this is Amazon advising you using machine learning as to sizing your table instance and other properties of your table to have best performance. You can have TTL on your data, time to live. Notice you have table status, creation date, the read-write capacity mode, and the sizing of the table, if you will. Notice here in the items, we don't have anything, so we can create an item. Again, I really have to emphasize how much I like being able to create items inside of the UI. It just really saves me time. So I'm just doing key value pairs. And then here, notice the data types. And then I'm going to click Save. Notice here's my item. And if I click into it, I can see the text or the tree. The text is in JSON. And notice I have a DynamoDB JSON, which shows me the allocated information here on lines 3, 6, and 9. Now, in terms of querying here is very non-SQL-like, so it's very important that you understand how to query. I could do a whole course on this. I really recommend that if you're going to use Dynamo, and you probably will if you're going to be in the Amazon ecosystem using NoSQL, that you spend some time understanding how to appropriately write queries and you actually read and practice the documentation. You'll just save a lot of developer headache if you do that. Notice here you have some ability to manage item level information. So TTL, so on and so forth. You can duplicate it. Next over here, we have metrics. So this is typical Amazon metrics console. Notice this is a subset of the metrics that you can see. Very important that you want to understand throttling because you maybe want to set the capacity. You're paying by capacity here. And this is serverless service. You don't care about servers. You don't care about scaling. You have some basic alarms here that don't have enough data at this point. But the idea is that you want to set alarms on when the table capacity is being reached. And here's your capacity setting. So you can use provisioned or you can use on demand. Again, very, very important. You're looking at a table as a service. It's a different kind of a model in terms of deployment, the serverless model that I find a lot of customers don't take the time to understand. And then either their table is not sized properly and their application stops, or worse, their table is not constrained adequately and they get too big of a DynamoDB bill because they haven't thought through the patterns of their data usage and they're just throwing all their data in DynamoDB, and that might not be the best design for certain cases. Indexes are a really important topic in terms of effective querying in Dynamo beyond the scope of this course, but I feel like I'd be remiss if I didn't mention this. Some new capabilities. We have the ability to create global tables for DynamoDB streams. Again, a lot of new functionality coming in here to support stream-based eventing solutions. Backups is within the past 12 to 24 months, including point-in-time recovery. Originally, the thinking was this is just, hot data that flows through your system into some other more persistent store, like an eventual relational database for some of the information or maybe a file system. But more and more people are using Dynamo as a core database storage for their application. We have contributor insights, triggers. And another thing I want to talk about is DAX. So DAX is in response to competition of in-memory, large NoSQL type of stores. Not just Redis, other ones as well. They call them accelerators. So Amazon calls DAX DynamoDB Accelerator. The idea is to extend the functionality of Dynamo rather than have to go to another accelerator or customized NoSQL solution like Redis. Keep it all in Dynamo. So in other words, make some of your tables be in memory. And I think this is actually just very, very astute on Amazon's part, because they are really understanding the challenge of learning the different NoSQL databases. And I think that's one of the reasons why Dynamo is and remains a market leader in the NoSQL world, because Amazon has really been very proactive in adding customer features, whether backups, whether in memory, whether, machine learning to analyze the setup of the table. It's a really innovative service. So I think in terms of cloud NoSQL, it's really very important to use DynamoDB as kind of one of the standards in terms of what is occurring. And this idea of consolidation is really quite fascinating to me. I've had several customers use DynamoDB for all of their NoSQL needs in their solution, and it's worked really well for them. Let's look now at a reference cloud document NoSQL architecture. This one was actually published by Amazon, but interestingly, I'm an advisor to a startup, actually a couple startups, but a startup that built using this pattern. And so it was really interesting to get feedback from the team on how it worked for them. It was their first cloud application, and they recently got funding and launched. So it's been pretty exciting to see their success. So first of all, the application, scalable mobile customer application. It's using the events pattern, so the streaming events pattern, and it's using mobile, and it's built on the Amazon ecosystem. So this particular one is using the Cognito serverless user authentication service on the front end. And important for our discussion in the back end here, we're using a document NoSQL architecture. So what does this look like? It's actually amazingly simple. So what has been interesting in the mobile development space is the implementation of frameworks which sit on top of cloud-based services. For Amazon, that framework is called Amplify. So the Amplify framework is designed to enable mobile dev teams to get applications up and running on top of Amazon's set of services, and including, importantly, NoSQL services really, really quickly. Using the Amplify framework, the team that I mentored was able to get a prototype up and going in less than 2 weeks. And in a couple of months, they were actually able to get their first round of funding because they were able to have users and show revenue. So the key services that Amplify abstracted away from them was Cognito and Dynamo. It was actually really interesting to see that they thought in terms of a data-first model, which they built in the Amplify interface, and then building that model, in other words, creating the structure, so customers table and whatever fields or columns would be in that table, would then build tables in Dynamo. And really, until we got to the point of diving into the performance of the application, they were aware the Dynamo tables were there, but they were really working at a higher level. They were working at the Amplify level. So it kind of reminded me of the days of having object relational mappers in the relational database world when we had layers up above the databases. But this was interesting because it wasn't just database, it was other services as well. So in any case, for this particular solution and others that I've seen, DynamoDB really is all things to the application. It is used for key value storage. It's used for document storage. There are some tables that are using the DAX accelerator, so they're in memory. They're hot tables. So I think growing trend I see having these vendor services, and most of them are serverless, just be the sort of all-in-one NoSQL store on that vendor platform. Now, that's not to say that using other databases such as MongoDB or Redis or Cassandra would be a poor choice. It's really all about speed. And because Amazon and Google have been quickly building features into their own NoSQL services, it's becoming increasingly difficult to find value in services that are built outside of these ecosystems. So it's a real interesting sort of situation because on one hand, of course, you don't want to get locked into the vendor, probably, but the service differentiation is so great that it's hard to justify not using that vendor's offering. So in this particular case, the DynamoDB ecosystem provided excellent value. To open this section, here's a quote from Eric Schmidt from Google. There were 5 exabytes of information created between the dawn of civilization through 2003, but that much information is now created every 2 days. In this section, we're going to analyze customer activity with NoSQL. We're going to look at graph databases, such as Neo4j, that store data and, importantly, their relationships between the data items. This is defined as nodes and edges that are stored in graphs. However, there's more than one format, as we'll see. And these graph databases are used to store graph-based data. And as all other NoSQL type of databases, they're extremely fast for relationship queries and easily scalable, but by default, they're not transactionally consistent. So what does this data representation look like? And this is from a vendor documentation for graph databases. You can see it's the entities. So John, Andrew, Sarah, for example. And they can have metadata such as labels, users in this case. They can have properties such as John has a username, a city, notifications, and a registration date. But the important difference in a graph database is in addition to the entities, labels, and properties, the relationship between the entities is also stored. So we can see John follows Sarah, for example, and John likes "it is the East and." So some kind of quote, I guess. So the idea here is you're storing both what I call the nouns and the verbs, the entities and the relationships. It's been really interesting to see that Amazon has jumped into the foray here relatively recently. For a long time, the leading graph database, and the one that I use with all my customers, was Neo4j, open source or commercial, and it supports property graphs and is queried with a Cypher programming query language. Within the past 12 months of this recording, Amazon has released NeptuneDB that supports graph-based data in two formats. Has two different query engines. One's called Gremlin, and that supports CSV-based property graphs, and another's called Sparkle, and that supports triples or quads, RDF, or turtle data formats. So there's a lot of complexity in these two graph contenders, and you might wonder, why is this needed? Well, graph database space in NoSQL is one of the remaining, in my opinion, more open areas where there's a lot of development, because as data volumes increase, storing the noun verb or storing the entities and the relationships is still rather new for many of my customers. And so there are different sort of use cases out there. Despite the graph database landscape being relatively new, we still have our 1, 2, 3 choices. So open source, Neo4j, free, requires servers, and you have to provide support and tooling. At the enterprise level, there's a commercial version of Neo4j that's licensed. It still requires servers, but they supply the support and the tooling. And relatively new on the block, we have AWS NeptuneDB, which is a managed service, and they supply the support and tools. So let's start by taking a look at a pattern that we've seen throughout this course. And this is a vendor or a Google optimized implementation on GCP. So in the GCP console, I've typed Neo4j, and you can see we have a lot of different configurations to pick from. The one that caught my eye was the casual cluster. So let's take a look at it. What this does is this is a Kubernetes app. So this uses containers. And for those of you who've done any work with Kubernetes, that's a whole set of learning steps in and of itself. And then if you layer on properly setting up a distributed NoSQL database, that's a lot to do. So using a pre-configured setup out of the Google Marketplace can really save you time. And in fact, this one is pretty well done. So I actually spun it up, and it just took a few minutes because, of course, it's running on the Google infrastructure, and their implementations are really so fast to start up. And it supplies you with a testable cluster really, really quickly. So if you click Configure, what you get is a deployment, again, as we saw in earlier movies. You just fill out the UI here. Now notice there's 2 steps. The first thing you have to do is create a Kubernetes cluster. So you just click Create Cluster. That takes about a minute or so. And then once that is created, you'll get a progress bar here. Then you click Deploy. Now the reason Deploy is available in my implementation, it won't be in yours, is because I already have a cluster set up. So I could deploy another casual cluster onto that Kubernetes cluster. This would be grayed out in your case until you clicked this. So it's a 2-step deployment. So I'm actually going to close this just to make it a little bit simpler. And now I'm going to show you what the completed deployment looks like. So this took, maybe about 5 minutes to do. And what it does is it sets up on the Kubernetes cluster. And Kubernetes, of course, is backed by Google Compute Engine virtual machines. But you don't see that. It's basically all done for you when the Kubernetes cluster is set up. And then on top of that, the Neo4j casual cluster is set up. And you can see you've got some nice documentation here that tells you how to then access, because as with all the other NoSQL databases, you then need a client to work with. Now this becomes a little bit more tricky because you're not working with VMs here. You're working with Kubernetes cluster. And so you have to figure out how to connect to the appropriate node in the cluster. So you can see over here, to access the Cypher shell, the directions tell you to set the app instance name to the name you deployed. And the name you deployed here is this one, Casual Cluster K81. So you just change my graph to that value. And then, so you can see what this is doing here. You can see that what is happening is the Neo4j password is being set from the kubectl command in your cluster. You're getting the secret out, and that's being passed to the Cypher shell. And notice here, this is Docker container image that is registered on the Google Container Registry. So the Neo4j public casual cluster. And it really is just for learning. And you can notice that this is set up here to access this. And then you can either work from the command line, the Cypher command line, or you do have the option of accessing Neo4j in a browser. And it gives you the information on how to do that as well. Now, what I did is I opened up a separate page here. And let me just scroll up so you can see what this looks like. And you can see that the first line here is I got the container credentials. And then once I did that, then I passed the rest of this through, passing in the container name here. And then once that was run, then I was able to work with the shell. So the shell is available once the connection is made. And here then, in this particular cluster, I looked in the Neo4j documentation, and you can see that I have an overview in this cluster, and I have 3 different databases. So how I found that is I went to the documentation here, and I wanted to view the members of a casual cluster. So you can see here they are, and then I could work with the databases that were there, and then here's the databases that are part of the casual cluster. I could create a database and so on and so forth. And this is inside of the Neo4j manual. Also, some of you might be interested in how to import data. So inside of the manual here, basically the sort of canonical movies example, and they have the data that's here. So persons, movies, and roles. So you'd have to create these CSV files, put them in a bucket, and then you would import them. And that would be here where it says load CSV. This would be into a Google Cloud Storage bucket. So then you could run the canonical movie example. The thing that I was really impressed with this is how quick and easy it was to set up, and the fact that I could set it up on Kubernetes, which is a modern sort of infrastructure. So I really liked, again, using the marketplace. That's a pattern. And I really liked using a deployment, because when I'm done with this deployment, of course, what I can do is just delete, and it will cleanly delete all of the information. It was a really nice way to get set up quickly so that I could explore running Neo4j on GCP. Now for this next example, we'll look at Amazon. So here, if we type Neo4j, we don't find anything. And of course, you may remember from the earlier movie that Amazon has an alternative. And this is, just kind of similar throughout this course, where Google seems to be supporting the open source version, and Amazon seems to be creating an alternative version. Which one's better? You'll have to test to find out, but it is an interesting pattern. So their graph database is called Neptune. And to work with it, you click Launch Amazon Neptune. And you can see that you have different engine versions and then instance classes. And the instances are set pretty large. So again, be cautious when you're testing this. This is not set up for free tier or small instances, and tells you that right here. Neptune does not have a free tier. So be sure to turn it off when you're done if you're studying. So by default, you're going to create read replicas in a different zone. And then you're going to have a database identifier, and I'm going to call it NoSQL graph. And click Next. And here's the VPC subnet availability zone settings. I'll just go with the defaults. So for the DB cluster identifier, we're just going to leave it blank. And for the other settings, we'll just go with the defaults. I'm going to take off deletion protection. This is something that is a little bit annoying when you're testing. I understand from a production point, but if you don't take it off, you can't delete. So it's just an aspect of working with testing that you want to take notice of in the Amazon ecosystem. And I'm going to click Create Database. Now, while this is creating, I want to point your attention to the documentation. Again, the brevity of this course does not allow me to go super deep into the complexity here of working with Neptune. One thing I really want to emphasize, though, is this idea of which data model, Gremlin or RDF Sparkle. It's interesting to look at this because it seems to me that Amazon's going sort of a different approach than what Neo4j is doing, which is trying to be a graph database for all. They're trying to have multiple capabilities. One thing I did note in looking at the documentation is that it is A or B. It's not A and B. So you really have to study this and get it right if you don't know from having worked with your graph data which one's going to work best for you. I did have a client where I worked with RDF, and it was in the art museum space where they worked with RDF data in terms of identifying the artworks. So that was something I knew that they needed RDF data. In terms of using Gremlin, to me, that seems more generic and more like Neo4j in terms of what I call the noun-verb graph data. So my experience has been RDF is specialized, and you'll know when you need it. So let's go back and look at this and see how long this is going to take. One thing that I noticed that was interesting, was very modern, is this capability to have a notebook. And this is indeed a Jupyter notebook, and this is served up by the Amazon SageMaker ecosystem. And the idea here is that rather than having a client, I guess it would be a Gremlin client or a Sparkle client on a separate EC2 instance, you could use those libraries through a Jupyter notebook. And I just find this interesting because this comes to me out of the data science world. So my experience is that graph databases are often combined with machine learning workloads. And so I think that's where the notebook client is coming in. I think it's interesting they built it into the interface. This is a really new service, and as I was investigating comparisons, I noticed some criticism that there wasn't yet a graph browser built into Neptune. Neo4j is very well known for having a very rich graph browser, a visual graph browser. So I would guess that Amazon, as is typical, will continue to build out features. So by the time you watch it, this might be a little bit different. So I'm going to go ahead and pause this video here, and then when these instances are created, I'll come back and take a look at it. So it took about 15 minutes for this to complete, and we have 2 DB instances. So we have the NoSQL graph instance here, and then if we go back, we can see we have this second one as well. So basically what we have is we have a reader and we have a writer, and we have our typical sort of monitoring, high-level monitoring. And then in terms of clients, kind of interesting, here's the documentation. So you can set up your either Gremlin or Sparkle client on an EC2 instance. Or there's a new type of a client that, again, I'll let you explore on your own because it does take quite a bit more time to set up. So you can create a notebook. And once you create a notebook, you're creating a EC2 instance with a Jupyter notebook on it with some examples of both Sparkle and Gremlin. So that took, again, about another 15 minutes to set that up. And then you open the notebook and you'll have the section underneath it where you can connect as a client. So working with Neptune, really interesting, a lot of new capabilities. Again, when you're done, like any other service that you've tried out, because this is not the free tier, make sure that you remember to delete everything. In terms of looking at an architecture for a graph NoSQL database, let's evaluate using one for a scalable marketing customer analysis application. Again, we're going to have an eventing pattern. We're going to use social media feeds here. And the reason for using a graph rather than something like a document or a key value store is we do want to capture the relationships from the social media feeds. Who's friends with who likes what. We're going to have a custom query front end and a NoSQL back end. And interestingly, we're going to use the data lake pattern. I don't know if you remember when we discussed it earlier or if it's familiar to you. The idea is that you have an object store or a huge file system. So in Amazon, in the case of S3, in Google, it would be Google Cloud Storage buckets, and you apply layers on top of that. So that becomes your storage facility. So this comes out of the Amazon ecosystem, and this was from a blog post. And again, they have a CloudFormation template, which allows you to deploy the whole thing in the linked blog post here. So the idea is that you have users accessing a Neptune utilities and an Apache Gremlin client, so custom application on an EC2 instance, or it could be EKS, it could be Kubernetes, some kind of compute inside the VPC. And that is going to generate Twitter-like data into the data lake, so Amazon S3. And then that is going to interact with Amazon Neptune, which is going to use Gremlin queries over Amazon Neptune and perform an aggregation of the data that's been analyzed for relationships with the data that is just stored in the data lake. So Neptune is performing the analysis of the data in the data lake. Now, this is a pattern that I'm seeing more and more where a NoSQL layer is being applied on the top of a data lake because the ability to store massive amounts of data cheaply is really compelling. S3 storage is far cheaper than traditional, for example, relational database storage or data warehouse storage up in the cloud. So this pattern is interesting, and interesting particularly in using this graph database to retrieve the relationships and provide that information back to the application. Let's start with this quote from Thomas Davenport. Every company has big data in its future, and every company will eventually be in the data business. In this section, we're going to look at what I call specialty NoSQL databases. As the NoSQL ecosystem matures, it's interesting to see how the databases evolve to meet customer demands. And the top-level trend here is time-based events coming from devices. So in this section, we're going to look at specialty-built NoSQL databases that can store real-time events using NoSQL. And we'll start with looking at two versions of a GCP popular NoSQL event database, Firebase and Firestore. And the idea with this is we're going to store time-based event data. Depending on whether it's Firebase or Firestore, data will be stored and made available in either real-time or near real-time. And this is used to store event-based data, so jagged data, keys, and varying values. So it's kind of a variant of wide column and key value. And this is extremely fast for time-based queries and easily scalable. And again, it's not transactionally consistent. So within the past 12 months of this recording, GCP has evolved Firebase, very popular, into another option, Firestore. And we'll start by looking at these two. So Firebase stores one large JSON tree. It is a complex hierarchical structure. It's harder to organize at scale because it's a single structure. But the important point is it's real time and presence is supported. And it's designed to be used with mobile apps. This was actually an acquisition, and you can see this in the way that you work with it still today. Firebase is hosted separately from the GCP main console. Contrast that with GCP Firestore, which stores data as collections of documents. It allows for richer, faster queries at scale. It requires less data flattening, and it's designed for GCP applications in general. It is integrated with the cloud console. Here we are in the GCP console, and we've navigated to Cloud Firestore. Notice when you go to set up Cloud Firestore, there's two modes, and this is what I was just reviewing in the previous movie. There is native mode and there is data store mode. They have two different APIs. The scalability is different. App Engine support is different. The maximum write per second limits are different. Real-time updates are only available in native mode, and mobile and web client libraries are only available in native mode. So typically you'll pick this for mobile, in other words, Cloud Firestore native mode, and you'll pick data store mode for general applications. So if I select this, it is a one-time, one-way selection, and I'm going to select a location here. And I'm going to click Create Database. Now, while I'm doing that, I'm going to navigate over to the Firebase web UI, which, as I mentioned in the previous movie, because Google acquired Firebase, is still separate as of this recording from the GCP console. And you can see here the recommendation is also to use Firestore Although, if you scroll down, you can choose the real-time database if you want to. And this is the interface for it. It looks similar, but not quite the same. This is designed for very rapid mobile development, and it provides a number of services that sit on top of this real-time database. So now navigating back to the GCP console, I can create an entity, and I'm going to specify that this is a customer, and I'm going to add a property, and I'm going to set this property as indexable, and I'm going to add a second property, and I'm going to set this type to an integer. I'm going to call it some number, and I'm not going to index this, and I'm going to click create. So here I have my entity. Notice you can import from a backup file, export. As with the other managed data services, I have a dashboard where I can integrate this with GCP monitoring. Here are my indexes, and I haven't created any composite indexes, which would be secondary indexes in this case. Again, this is going to be based on your query patterns. And then you have administrative settings that are available here. Now we're going to take an overview look at what I think is really the future of NoSQL. And this is through the lens of IoT, or Internet of Things. I have quite a bit of familiarity with the AWS IoT ecosystem, having worked in a production setting a few years ago when the services were relatively new for over a year. And what has been interesting to see is how across the cloud ecosystem, whether it's Amazon, Google, or Azure, how these purpose-built systems are evolving because of demand. IoT is one of the big drivers and creators of data that would be appropriate for NoSQL, so event data. And it is challenging to work with using traditional data stores because of the limits of size. Also, the type of data is event data, which is sort of a classic NoSQL because you will have some values be populated in some states, but not always. So populating a traditional relational database with this data would result in data bloat. It would have a lot of nulls or basically empty spaces. And the data can be voluminous because the events generated by these IoT devices is non-trivial. So it's interesting to see how purpose-built systems abstract away the underlying NoSQL. As we'll see in our brief look here at AWS IoT, NoSQL is something that's being used, but you're not seeing it. So there is an IoT event database underneath AWS IoT. It is, if you read very carefully in their documentation, some kind of version of DynamoDB, but it is a proprietary version. And they're designed to store IoT event data. It's stored and queried per device. So there is device awareness built into the structure. You'll remember that classic NoSQL does not have any sort of schema or structure. So this is a hybrid type of a NoSQL because there is an underlying structure that is being applied. The idea is IoT event data will be natively stored. It will be extremely fast for IoT event queries and scalable. It won't be transactional because it's NoSQL. And in this case, it's going to be part of IoT Core. It's a set of services. And this is an area where innovation is occurring very rapidly. Very much possibility by the time you watch this, there will be even more services. Amazon has released, I think, 50% of this that is available as of this recording in the last 6 to 12 months. So there are many things to look at here. We're going to look at something that's really pretty new. It's called IoT events. And the reason I pulled this out is because it's interesting. When I was working in the production situation, we had to write all this. This was not a service that was available, and it took a really large amount of our development time. So it's just an example of cloud vendors paying attention to what the customers are doing and trying to provide value so that they can get to market faster. Had we had this service, I am very convinced that we could have developed faster and gotten to market faster, which was an important aspect of the work that we were doing because we had competitive pressure. So IoT events is a subset of the IoT core, which is a layer of abstraction on top of several types of NoSQL databases. And it actually provides a graphical design input. I'll show you it in the subsequent movie. But the concepts are you have device inputs, And then the IoT events service, which is serverless, like all of these new services, so you just pay by the consumption, helps you to monitor your equipment changes in operation and trigger alerts to respond when events occur. So, and it's an eventing mechanism. And you can define the conditional logic to evaluate the incoming telemetry data and then detect and trigger and set actions. So we'll take a brief look next at the IoT section of AWS, and then we'll drill into the IoT events section. Here we are in the AWS Management Console, and if we scroll down, you can see in the IoT section or Internet of Things, we have really a large list of services. The first service that typically you start with is IoT Core, and that allows you to set up your database and your connection to your external devices, and they're called things. So we'll see that referenced in the events section. You can see that we have a number of analytic capabilities, including IoT analytics. We have one-click, we have device defender, device management, Greengrass, which runs IoT on the device rather than in the cloud. We have Sitewise and Things Graph. We're going to drill into events because, again, it represents a layer of abstraction over the underlying NoSQL database that I think is interesting for IoT, and because it represents, I think, where NoSQL is going in terms of the value that the cloud vendors are providing. So inside of IoT events, we remember from the previous movie that basically it is a framework to help us to set up thresholds for events on our particular devices and actions. And this logic is called a detector model. So if we click Create Detector Model, and we have several to choose from here. And notice, interestingly, it's a visual interface. This is really a secondary abstraction. So we've got an abstraction over NoSQL, but now we have an abstraction that's not a scripting language or an API, rather a visual language. And I think this is particularly interesting because what I've found in working with IoT clients is, depending on what the device is, if it's a home monitoring device, if it's a case I worked with was a sprinkler controller device for commercial use, whether it's building control, you're generally going to be interfacing with device experts and sometimes also subject matter experts. So having this visual layer for communicating, I think, can get you to value faster. So we're going to work with a template, and you can see we have a number of templates here. So everything from, human heartbeats, for example, to event detections with sensors and applications. So we'll just click on that because it's using MQTT, which is a standard protocol for commercial IoT devices rather than TCP/IP, for example. So we'll click Start. And you can see here's our visual interface, and here's the start point. So it's a state model. And here we have the device in the state of idle. And you can see, again, it's a nice GUI. So we can define our eventing here. So on enter, on input, on exit. And then this is to our state change here. And you can see here is our event trigger logic. That is an abstraction layer that sits on top of our underlying NoSQL database that holds our device event information. And you can see when the variable position is not from the input IoT events, the blueprints tracking device input, you're getting a particular position. And then you can add an action here. So if we click Add Action, we can choose an action, and we can send a message to an IoT events endpoint, to Kinesis Firehose. We can trigger a Lambda. We can publish a new topic. We can use an SQS message, an SNS message, set a timer, set a variable. And then when the device is in use, again, we have the same configurable input here, and then we can go to an exception state. And over here we have our visual designer, so we can use this to add additional logic. When we're ready for this to be used, we can click Publish, and then this will be made available in our IoT eventing ecosystem. Again, I think this level of abstraction over NoSQL, number one, is really useful, and number two, represents the direction that I see the NoSQL ecosystem evolving, which is into domain-specific abstraction layers. Yet another innovation announced by AWS at last year's reInvent was a new NoSQL database to further augment IoT and other event scenarios. As of this recording, this product is not yet publicly available. It's in a private beta, but I wanted to include it because it is interesting. I am on that private beta. And by the time you see this, this may be publicly available. So the idea is to store time-based events with NoSQL, which is a very typical scenario for IoT. So time-based event databases, such as the newly announced AWS Time Stream. The data will be stored and queryable via time windows. Now, this is a capability that we've had in relational databases via windowing functions for quite a while. So you might wonder, what is the purpose of this? Why would we just not use a relational database? And again, this comes down to the key and core value propositions of NoSQL. You may be thinking, remembering that with IoT eventing data, a reason to use the IoT services is because of the volume of data. It simply would be too expensive to store that data in a relational database and too slow because the transactional capabilities provided by the relational database really just slow it down, add cost, and don't add any value. So the thinking behind this product is customers want the ability to query by time windows that they're familiar with from the relational world, but they want it at the scale for event-based data. So as Andy Jassy announced, the idea is that it will be 100 to 500 to 1,000 times faster on the volumes of data that customers are bringing in with their IoT solutions. So it will be extremely fast for time-based queries. And of course, being NoSQL, it will be AP of CAP theorem, in other words, highly available and importantly, very, very easily partitionable. Simply add an additional partition to scale out. This has also been announced, of course, to be serverless, which is the direction that the cloud vendors are taking their custom NoSQL implementations, which again makes it really interesting because you can simply pay for capacity and not worry about setting up servers, configuring high availability. All that is included in what you're getting from the vendor. So I haven't seen competitive time stream type databases yet available from the other cloud vendors. So I think this will be an interesting area to watch as Amazon leads here and to see what the adoption is around this solution. It is very specialized and, there's always the trade-off between usability because there will be optimizations available here that are specific to the NoSQL world. So you'll again have to consult the documentation, understand how to do the optimization, whether it's partitioning, indexing, or whatever it is when it's announced, versus leveraging knowledge that you have from either the more conventional NoSQL world or the relational world. But I think it does bear watching, it does bear trying out if you have this scenario. So AWS Time Stream. The next type of NoSQL database is designed to store blockchain data. An example of this is Amazon QLDB, or Quantum Ledger Database. It is used to store blockchain event-based data in an immutable or unchangeable journal. It is extremely fast for blockchain event-based queries and easily scalable. And it's part of AWS Managed Blockchain, which is a set of services. Now, it's not required that you use QLDB with Managed Blockchain, and there have been some interesting customer scenarios that Amazon has been documenting in their series with Werner Vogel's traveling around the world, mostly to developing countries, where there's been some interesting uses of QLDB for its immutability because it becomes a permanent system of record. However, it can be used and is designed to be used in conjunction with AWS Managed Blockchain Services, which again were released last November at reInvent. Now, QLDB has a number of concepts which I'm assuming are new to most of my viewers here. And so we'll just cover a couple terms before we dive in and take a look at the actual service itself. So it uses at its core this idea of an immutable journal. So one of the foundational principles of chain-based computing is having a journal that has all changes recorded for all time and is unalterable. So some of the core concepts here is each set of changes or each document is called a block, and a list of those changes in QLDB is called a strand. Along the strand, each of the blocks will have a sequence number, and it will be protected by a hash. And as you traverse the strand, you will be able to work with document revision histories. So one of the things that I like about the Amazon implementation of QLDB and blockchain is they have a very useful tutorial. Now, the full tutorial for blockchain itself, first time I went through it took me a couple of hours because the concepts were new and I wanted to stop and look up concepts. Probably if I just clicked through, I could do it faster. So I would encourage you, if you're interested, as I am, in these technologies, to use this as a starting point. Next, we'll take a look at QLDB, but we'll round that out and I'll point you to the blockchain tutorial because I think it really is well worth doing to get a basic understanding of how these services work in general and specifically on the Amazon ecosystem. Here we are in Amazon QLDB. And notice we can create a ledger or we can start the tutorial. Again, it has a pretty good description of how this works. Talks about the journal and the current state and the indexed history and the cryptographic verification. So we're going to actually start the tutorial. So there are a couple sections here. The first thing is we're going to create an empty ledger. And we're going to call it vehicle registration. We could put tags on it. We're not going to bother to do that. We're going to create the ledger, and it's creating. Notice it says it may take a few minutes to become active. Now our ledger is created. So we're going to go back to the tutorial. We're going to refresh, select our ledger, and we're going to load it with sample data. Now that's completed. And we're going to open the query editor. We're going to select our ledger, and we'll see that we have some information that's been populated. So we have vehicle information, driver's license, registration, and person information. Now we're going to query the information. So we're going to copy this query, paste it into the editor, and we're selecting the vehicle information for this VIN. We're going to click Run, and we'll see that we have one result. And you can see this is from the tutorial, the associated tutorial. So we'll just run a second query just so you can see how this works. We're going to join the vehicle with the vehicle registration to get related information. Copy the query, paste it in, and there's our result. So now back to the tutorial. We could also verify the integrity of a document in the ledger journal by using cryptographic hashing with SHA-256. If we want to see that information, we can open that up, and then we could perform the steps here. We could go to the ledgers, and then we can get the digest. And there's our digest. Now, in addition to this tutorial, I recommended in the previous movie that you may want to also do the managed blockchain tutorial, which, as I was saying, took me a couple of hours because I wanted to make sure I understood all the concepts. I think if you just ran through it quickly, it would be faster. To summarize, Amazon QLDB does not require that you use Amazon blockchain, but these two are often used together. Peter Sondergaard from Gartner says, information is the oil of the 21st century, and analytics is the combustion engine. And this is reflected in the evolution of NoSQL in the time I've been working with the ecosystem. The first big trend I'm seeing is consolidation of the NoSQL market. I'm observing that open source-based companies seem to be declining in number and in market adoption, and they seem to be being replaced by either cloud vendor supported versions or by cloud vendor replacements. I'm also seeing consolidation by mergers of the NoSQL companies. I'm further observing consolidation by current NoSQL products, such as Redis, for example, adding features. NoSQL databases that were started in one category, key value in the case of Redis, are adding capabilities in some of the other categories, such as documents or wide column. And I'm seeing the preference for customers that want tools and support and the movement away from pure open source, because many customers have felt the pain of trying to support the open source versions of the products on their own. When I think of the NoSQL market, I think of the 4 core types of NoSQL databases shown here as key value, column family, graph, or document. But I also think of the other types that I've shown in this course, what I call blended NoSQL, so key value plus document, for example. Importantly, events is driving the evolution of the NoSQL ecosystem. And I think it's really interesting to see what the vendors, and I've paid the most attention to Amazon because that's where I've done most of my production work, has done in this space in terms of time streams, near real-time, and IoT abstraction layers. Support for blockchain technologies is also really interesting coming from the cloud vendors. And we did take a look here at Amazon's relatively recently released QLDB or Quantum Ledger database. Probably, though, the most interesting aspect of the NoSQL ecosystem is a subtle one. And this relates to what's going on in Google's implementation. I think it's best represented by Google BigQuery, which many would argue is not a NoSQL service because you use a SQL query layer. However, if you read the underlying implementation, it is indeed built on a massive NoSQL store in Dremel. So what I think is fascinating is it appears to be almost a circular evolution in that because of the pervasiveness and the usability of the SQL query language, whether the various NoSQL stores implement a SQL-like query language, so everything from CQL with Cassandra, all the way to a pure ANSI SQL language in Google's BigQuery, adding a more SQL-like query layer does really impact the usability of NoSQL, and it's something to pay attention to. And another aspect of the NoSQL ecosystem that I think bears watching is the move to the cloud. As you would know, since you've watched this entire class, this has been a complete restructuring of an earlier version of this course where I did not focus on cloud versions of NoSQL databases because they didn't exist. So this has been, over the past 3 to 4 years, a pretty significant shift in the market, led by, as usual, Amazon and Google. They're creating either supported versions of NoSQL with migration paths, such as Amazon's Document DB, which they say right in the description supports Mongo and has a migration path, to alternatives such as GCP's Bigtable, which many could argue is the evolution of both Mongo and Redis into a key value wide column, massively scalable, cloud native for Google store. I find that the vendor implementations, because they're built by the vendors, they're built to work with their clouds, are much easier to work with. And given for many teams the amount of new information they have to process when they're working with NoSQL, whether it's how to store, how to query, how to optimize, I find faster time to value. And I generally will prefer working with the cloud vendor solutions rather than the open source. Particularly, I will prefer it if the cloud vendor is offering a serverless solution. I think Amazon DynamoDB is the quintessential example of this, and I think that's why DynamoDB takes the lead in the cloud-based NoSQL market. It simply is easy to use, provides a lot of value. Amazon is constantly adding new features that customers want, from point-in-time backups to the ability to put tables into a global location or in memory. Really, the amount of innovation here is benefiting all of us. Continuing on evaluating the evolution of the NoSQL ecosystem, looking at multifunctionality is really important. When I first got into this game, many years ago, I would say, all right, I need a key value store, so let me pick Redis. I need a document database, so let me pick MongoDB. Now it's really not that simple because both MongoDB and Redis can be both key value and document and more. So what has really happened is instead of having 150 different NoSQL databases, we're having maybe 5 that are relevant. And those 5 are adding layers of features. Another key set of features is in-memory options for those NoSQL databases that weren't natively in memory. And I think, again, DynamoDB from Amazon represents kind of the direction there. Customers are wanting to be able to utilize the memory of whatever hosting environment so that they can serve up even faster. Enterprise features are key, whether they're backup, monitoring. Google has had an interesting direction in terms of integrating versions of open source products, such as Cloud Memory Store for Redis or Neo4j or MongoDB, for example, and integrating them so that Google's enterprise monitoring Stackdriver, in their case, will integrate with the performance counters in the particular NoSQL databases. So it's one monitoring solution. And again, this provides significant value in production applications. Another interesting trend is abstraction layers. We looked briefly in this course at IoT services and eventing, and I mentioned Amplify in terms of my mentorship of a startup. It was really interesting to work with that startup team and to see, as I mentioned previously, that when they first started, they were actually completely unaware of what their database was because it was abstracted away through Amplify. It was indeed DynamoDB. And at some point, of course, when they were debugging and building their application, they needed to realize that and go to Dynamo. And some people might argue, that's not a good thing because when you are building, you will invariably run into challenges. And if there's too much abstraction, it becomes difficult to find where the problems are. But, I did see this team get to value. And of course, Google has the entire Firebase ecosystem, which is somewhat similar to Amplify. The idea is to abstract away the database so that you can work on the application code. Now, summarizing cloud NoSQL databases and kind of the way I think about it from an architectural standpoint is this chart. And you can see in the key value world, of course, Redis leads the open source charge. I think of DynamoDB, and I note that it's serverless on AWS. For GCP, I think of Memory Store for Redis. In the columnar world, Cassandra is the standard and open source. Of course, Amazon has the new managed Cassandra product, and they also have their data warehouse Redshift. I'm really hoping that they add a serverless component to that because I think it'll help it to be more competitive. In the GCP side, we have Bigtable for hot data and BigQuery, which has the interesting SQL layer over the top of it for a data warehouse or aggregate queries. And I think in this category, Google really has a very interesting offering because both of these services are very fast, very usable, serverless, and very compelling. And I use them with a lot of customer solutions. In the document world, MongoDB is the open source standard. Amazon has Dynamo and the newly introduced DocumentDB, I think really to give customers a migration path. Google's offering here is managed MongoDB. I think that they really see their customers using Bigtable, and that's what I tend to do rather than a Mongo solution on GCP. In the graph world, we have some interesting new services to compete with the open source standard Neo4j, notably in AWS Neptune, which you may remember provides not one but 2 different graph models, both the Gremlin model and the Sparkle query model. Google offers managed Neo4j. I do see the growth of graph database demands from my customers, and so it'll be interesting to see what happens in this space. I think there's more to come. And then a lot of interest in the events IoT space. Amazon's coming with TimeStream. They have now already IoT events, which is serverless. GCP has strong offering there with Firebase, Firestore, and they do have IoT Core. And again, all this is serverless. On the ledger side, we have Amazon with Hyperledger offering on blockchain. And then as far as pure ledger database, they have the relatively newly released serverless QLDB. And I think it's very significant here to note that the trend not only is to offer alternatives to open source on the cloud, but to offer serverless alternatives. I think that's just really very significant. And when you are in the process of evaluating what's going to work for you, You want to do side-by-side bake-offs, and when you have the opportunity to have serverless, you really can have time to value much more quickly. Now, although this course covers NoSQL, in my work as an architect, I am often asked to discuss another alternative in terms of big data processing, and that is data lake. So it's really beyond the scope of this course to go deep into it. I do have some other courses in the library on these technologies, and I would really encourage you to also include learning about these technologies, because increasingly as the volumes of data become very, very significant, data lake becomes a relevant part of an ecosystem that probably will include NoSQL. So although I call this data lake alternative for the NoSQL market, I might also say data lakes plus NoSQL. So a couple of trends that are significant here: the Hadoop ecosystem, which is distributed data processing at huge scale, has really evolved into in-memory via the Spark ecosystem. And I would recommend that, again, if you're working with file-based solutions that are huge-sized, you might also want to take a look at some of these technologies. I've been doing quite a lot of work, for example, with genomic data for bioinformatic research, and nearly every customer that I work with there is using a combination of Hadoop Spark and NoSQL. In this data lake ecosystem, Spark dominates, and then we'll add NoSQL-like functionality and sometimes SQL on top of it as well. Cloud-based data lakes from vendors like Amazon that are built on object stores such as S3 will replace the underlying proprietary, expensive, hard to maintain Hadoop distributed file system, or HDFS, for many of these data lake solutions. In fact, Amazon actually introduced a set of services called Amazon Data Lake last year at reInvent to help customers get time to value more quickly when they're building data lake technologies. Google, again, is taking the lead. They seem to always be pushing the market forward in terms of technology, which is, again, good for all of us. They have moved well beyond Hadoop, which is ancient by Google standards, 15 plus years old at this recording, to a commercial implementation of their next level unified API, which is called Apache Beam. That part of it, of course, is open source. They built a distributed data processing service on top of it called Dataflow. And you'll see throughout Google reference architectures and ecosystems that when they have massive big data projects, they'll use a combination of Dataflow, which will operate on Google GCS buckets as their data lake, and then they will process with various types of technologies, including Spark, but also including NoSQL functionality, which for them would often be BigQuery, which I know is very ironic. It's NoSQL with SQL. But I think in many ways, as I've said a couple times in this course, this actually represents the future of NoSQL. In other words, a NoSQL backend with a SQL front end. And they've expanded BigQuery substantially over the past few years. They've added the ability to do inserts, updates, and delete, or CRUD operations. They've added the ability to add functions. And interestingly, they've added machine learning. So it becomes really the query layer on top of the data lake. And in some ways, it makes working with NoSQL not necessary sometimes in GCP. It's really interesting to see how the market moves. The trends around cloud and consolidation and data lakes, I think, are very important when you're considering your NoSQL choices.